as is. Right. All right, so let's press ahead. So let's continue. So, all right, so you're given this. So blue and red light are incident on a perspex block as shown in figure 3. Calculate the angle of incidence for each color of light. Alright, so calculate the angle of incidence for each color of light. Alright, so you have to remember now in terms of angle and angle of incidence or angle, all the angles are measured from a normal. Alright, so if my attempt at drawing a block. So if you have a medium like this and light is hitting it at the top, the normal is just an imaginary line that's perpendicular. So it's at 90 degrees to the boundary. So that's a normal. So you have to look if they did put in a normal in the question. Alright, so all angles are measured from the normal to that ray. So if from the normal to the incident ray, if it's reflection, it's going to be like that. If it's refraction, it's going to be entering the medium. But in any case, you still have to draw a normal. So let me go back to the image. So let's move over this chemistry. Alright, so this should make this one a bit clearer. So calculate the angle of incidence for the blue light. Alright, so for blue light. So let me try. You see 17 degrees and you see 53 degrees on this. This is 17 and you see 53. So might as well just draw it on this thing. Alright, so let's say that represents blue light. And this one represents the other one. So you are told that this is 53. Oh, sorry. I'll move this back. You're told that this is 50. I can't write the 53. Alright, let me write it outside and then move it. 53. And then in here is 17. So this is the blue light. So so they wanted the angle for blue light, the incident angle for blue light Is the incident angle the 17 degrees? Is the incident angle the 17? So this is the, or the 53. Is the incident angle the 17 or the 53? Do you think that's the answer?
Definitely not, sir.
It's not. Alright, so what you would have to do in a case like this is put in the normal. So this is geometry and trigonometry. So if you put in the angle between the normal and the boundary is 90 degrees.
Yes, sir. So we can use the value of 53
Mm-hmm.
and subtract it from 90, which would get 37, and that would be the remaining
So
angle to the
37.
normal, sir.
So 37 would be this one. 37, oops,
Yes, sir.
would be the one that's missing. So 37 degrees. So the 53, 90 minus 53, that is your incident angle. The angle that's measured from the normal to the blue ray. Alright, make sure you're okay with that. If you're not okay, let me know. So 37, that would be 37 degrees. Alright, what about to the red light? So the red one is here. Is the second line. What would be the angle for
Sir, it's just an addition of 37 and 17 degrees, which would
7,
get 54 degrees.
54? So it would be the 37 that you just found plus that 17 that was there. So 37 plus 17 for. Alright, so the incident angle for blue light is 37 degrees, and for red light is 54 degrees. Alright, so hopefully we'll all see that. Alright, the next one is to calculate the angle of refraction of the blue light given that the refractive index is 1.53. Alright, and I think they kind of made a little error there because it's not the refractive index of the blue light, it's the refractive index of the perspex. But still do a calculation. Perspex is just a type of glass. So angle of refraction, we can use our Snell's law. So sine I over sine R is equal to N. So we can use our Snell's law for this. So sine I over sine R is equal to N. Alright, so you just do your substitution. So state the formula first. So don't just start calculating. State the formula you're using first, and then you substitute. So it's state, substitute, and solve your solution. So For blue light, I think that one was a 37. So it would be sine 37 is equal to, well, sine 37 over sine r. Sine r is the unknown. That's the one they wanted to find. So I'm just substituting what we know. Sine 37 over sine r is equal to 1.53. So you transpose, so people transpose different ways. So you transposing to make first, well, we want to make r the subject, but we can just make sine r the subject first. And then, so if it's something in the denominator, some people transpose by getting the thing, if the subject you want is in the denominator, you could multiply both sides by sine r. Alright, so that's one way to transpose. So you would end up with sine 37 is equal to 1.53 times sine r. And then you can get sine r by itself by getting rid of the 1.53. So you can divide both sides by 1.53. So you would get sine r is equal to sine 37 divided by n. So we can, somebody, I hope you guys have your calculators close to you or use a calculator. So find what sine 37 divided by 1.53 is.
Sir, 0.39.
Okay, so that's 0.39. Of course, that's not the angle. So if you get a value like that, kind of suggests that you're not done. So we'd have to know the sine inverse too, because it's r we want, not sine r. So we need the sine inverse of that.
Sir, which would give you 22, we'll call it 23 degrees. Because it's 22.9544 degrees.
22.9. So all right, 23 degrees. All right, I remember your, make sure your calculator is in degrees. So it might sound like a simple thing, but make sure your calculator is in degrees when you're doing these calculations. So you might want to start getting familiar with your calculator. Don't wait until um, the exam, or else you get a new calculator, new fancy calculator, and then know how to manipulate it. So I was going to write sine 37 over 1.53. Alright, so that's how you would calculate. That's how you would calculate the that. Okay, so the way they're writing this question is so wrong. But anyways, we can proceed. Calculate the critical angle for the blue light. Again, it's not for the light itself, it's really for the medium. So they really phrase this question so wrong. But nevertheless, let's proceed. So critical angle, remember the equation for critical angle to find critical angle? What's the equation to find critical angle? So it's not sine I mean, it comes from sine I over sine r, but there's a simpler way to do it. Alright, so critical angle is sine c. So make sure you remember this. Sine c is equal to 1 over n. That's all. Alright, 1 over n. That's how you calculate the critical angle for any material. So if you know the refractive index, you can calculate the critical angle. Alright, so the critical angle for this is going to be, we know that the refractive index is 1.53, so calculate what 1 over 1.53 is. What's that equal to? So that's sine c. Sine c.
Sir, it's equal to 0.65.
0.65. Alright, so therefore c, what's c
Is
going to be?
equivalent to 40.5 degrees
40.
or 40.54 degrees.
Alright, 40.5 degrees. Alright, any problems with that? So okay with that. So once you know the formulas for this, you should be good. Alright, what's the significance of the critical angle? What concept is it usually linked to, the critical angle? What's the significance of it? For anybody who remembers.
Sir, if I remember correctly, the critical angle is the point where the angle of refraction is equivalent to 90 degrees. And once you exceed the critical angle, you're going to get total internal reflection.
Great. Alright, so that is it. So the critical angle, let me see if I, alright, I was going to bring it up. Let me see, wave, optics, wave, okay. So let me just show you quickly. So you need to know the conditions for total internal reflection. The conditions for total internal reflection, one, you have to have the light moving from a dense medium to a less dense medium. So you won't have total internal reflection if it's going from like air to glass or air to water. It has to be going from the denser to the less dense medium. So that's the first case, as well as the your angle of incidence, or the angle of incidence, must be greater than the critical angle. So you can calculate the critical angle for any material once you know the refractive index. So water is about 1.33, glass is about 1.5, diamond is about 2.4. So diamond, which has a very high refractive index, would have a lower critical angle. So it's easier for total internal reflection to occur in diamond. Hence why it's
That's why it's so shiny.
right. Right. So that's the significance of the critical angle. Alright, so let's see if they ask you about that or they just leave it alone. Alright, look like them leave it alone. But sometimes they will go on to ask you about the total internal reflection. Okay, let's do this one because this one is a little different. Alright, figure 5 shows a coin at position O in an empty container. An observer is unable to see the coin based on the position of his eye. Describe how the observer can see the coin when the container is filled with water. So you can, yes, go ahead.
So when light enters the water, though, because of the refractive index of the water, the light rays would refract and therefore exit the when it hits the it would refract once it enters, hit the coin, and then refract out of the water. Yeah, reflect out of the water, reflect and refract out of the water and enter the eye.
Right, so this is based on refraction. So once it's now filled with water, it's not that line that you're seeing there is not going to be straight. Yes, go ahead.
Isn't it refraction and reflection?
If it's both, it's
Yes, sir.
refraction. It's refraction. So we know light travels in a straight line. Um, so we're talking about in this image there's no we call it change of medium. But if you add water to the container now you're talking about the
But sir, for
light
you to see something, something has to reflect. Light has to reflect off a
of the
surface of an
coin.
object.
Yeah,
Yes.
yeah. So it's reflection in that sense, and but I was specifically making mention of as it moves from the water to air, that refraction. Alright, so you'd have to mention both to get the 2 marks here. Yes, go ahead.
So it's okay to mention that it's reflection that's needed so the coin can be seen, right?
Reflection.
Yes, sir.
Alright, you remember what you had said before? Repeat what you had said before.
I originally mentioned that when the light enters the water, because of the refractive index, when the light ray hits and reflects off the coin and refracts out of the water and then into the eye, it would seem as if the coin has moved, something like that.
Okay. Right. So what I was saying is that you have to explicitly mention refraction as well, the bending of light. Alright, so don't just limit it to reflection. So when the light rays hit the coin and then it moves out of the water now, then you're going to have refraction happening, or light moving from air to water, refraction is going to happen. So you have to mention both. So that's what I was saying. Alright, and then we go on to, so this one is a little different. This one is a little different. So we know that the refractive index can be calculated not only using sin I and sin R. There are different things we can use to calculate refractive index, or we can relate the refractive index to. And one of them is speed. What is another quantity that we could have related refractive index to? So apart from the angle and apart from the speed, what else? What's the third thing we can relate it to? If I remember. Yes, go ahead.
Sir, is it pressure? Atmospheric pressure?
Pressure? No. It's a characteristic of the wave. Yes, go ahead.
Could you please repeat the question?
I was asking what else apart from the angle and apart from the speed, what else can you relate the refractive index of a material to? So I kind of showed you an equation a while ago. So I don't know if you remember that equation. Alright, so we can also relate it to the wavelength, is what I was saying. Alright, so wavelength, they could have given you wavelength values as well.
I'm confused by the question, sir. You are asking how you relate about
I
refractive
said,
index.
what else can you relate the refractive index to? So Snell's law is about relating the angle of incidence and the angle of refraction to refractive index. But you can calculate refractive index using other quantities. So that's what I was asking about. What other quantities can you use to calculate refractive index? So is the question clear now?
Yes, sir.
Alright, so let me just rewrite. That's right. Rewrite. So we can calculate refractive index. So n is equal to sin I over sin R, or it's also equal to V1 over V2, or it's equal to lambda 1 over lambda 2. Alright, so that's all I was asking. So when we go to this question, so look at part 2. What do they want you to do here? What are you trying to determine in this situation? What are we trying to determine? Which relationship are we going to use here for this one? Are we going to use sin I over sin R for this one?
Velocity, initial velocity over final velocity.
Alright, so the V1 over V2. So, alright, so you're told that the refractive index is defined as the ratio of the speed of light in air to the speed of light in water. So they actually told you the equation in words. So calculate the speed of light in water. Alright. So we can substitute. So it would be V1 over V2 is equal to N. So which one we know? Which one we know? So V1, which one we're trying to find? V1 or V2 based on that scenario. is equal to n. Alright, and since it's the speed of light, we could have also used c as well, c over v2, but they have to complicate it. So yeah, so the speed of light is going to be v1. Speed of light in air, I should say, is v1. So that's 3 times 10 to the 8. So 3 times 10 to the 8 meters per second over v2 is equal to, refractive index was I think 1.3, so let me check again. Refractive index, yes, so it's water, so the refractive index that they give you is 1.3, so use whatever they give you, 0.3. Alright, so if you're making v2 the subject, what would it be? So before you even give me a value, what's the transposed equation or transpose thing? Yes, go ahead. Yeah, go ahead.
Sir, V2 would be equivalent to V1 upon N.
So v1 upon n, so you're saying it's 3 times 10 to the 8 over 1.3. 3 times 10 to the 8 divided by 1.3. Alright, so what's the new speed? What's v2? Alright, yeah, so do that calculation.
Yeah. Sir, it would be 2.3.
So 2.3
2.3 times 10 to the times the eighth power of 10.
so 2.3 times 10 to the 8, and unit, make sure your unit is at least in your final answer. So speed, meters per second, or ms to the -1, so don't leave off your units. Alright, so we looked at that. Alright, let's look at some lenses for a little bit, since we're dealing with a bit of optics. We can look at some of the lens concepts. So lens equation, make sure you're familiar with the lens equation. Let's take off this side. So 1 over the focal length is equal to 1 over u, which is the object distance, plus 1 over v, the image distance. Alright, I usually use v, like virtual image, to remember that v is image. So 1 over focal length is equal to 1 over object distance plus 1 over image distance. Alright, and then magnification. The magnification is the image size over the object size, or the image distance over the object distance. But one thing you can't do, you can't mix them. So you can't say the image size or the image height. You can't say the image height divided by the object distance. Alright. So do we know what they mean by image distance and object distance? You know what all of those mean? So we have some images below that. So we have a convex lens. So we're talking about the distance of the object away from the lens, or the distance of the image away from the lens. So that's what I mean by object and image distance. All right, the height, of course, you're measuring the literal height of the image formed, or the height of the original object. So you have this table. This little table. It's useful. So I'm going to show you how to use that table. Alright, that one is a graph. I'm not going to look at that graph one yet. So let me just do a quick example of using the lens formula. Somebody had a question?
I'm right here. It's a bit. Oh, I love your hair. How are you?
Check your mics,
I saw it in. Na classe din? Yes. What is it? So Arizona is the super. And
Oh, I had it in a separate one. Alright, let's continue. So we're going to do an example how to use the lens formula to calculate image or object distance, or whatever it is, or focal length. So 1 over f is equal to 1 over u plus 1 over v. So in this question, what is u? What is u? What's the value of u? So if you remember what u is, what is u and what is v? So start with u first. Which one would represent u, that distance? $15 centimeters. Alright. As the very first question says calculate the image distance v, so it must mean that the other thing there is u. So the lens equation says, and the focal length is 10, as I said. So the lens equation says that 1 over f is equal to 1 over u plus 1 over v. Alright, so focal length is 10, so it would be 1 over 10 is equal to 1 over 15 plus 1 over v. Alright, so if you want to make v the subject, what would you do if you want to make v the subject? What's the first thing you could do? So we're doing some maths now. So that's maths we're doing now. Yes, go ahead. Oh, Reciprocate meaning, well, you have to be careful when you're adding, if you say reciprocate and you're adding for. Uh-huh. Uh-huh. All right. All right. So let's try one of those methods. So you have 1/10. We could get 1/v by itself. So that that reciprocal thing sounds a bit tricky. So I if I was doing it, I would just move over the 1/15 and just leave the 1/v there and leave the reciprocating till the end. So you could literally put 1/10 in your calculator and 1/15 in the calculator, and that would give you an answer. Alright, I think I'm more comfortable with that. You're less likely to make errors. So what's 1/10 minus 1/15? So work that out. So you could literally just say, you could work them out individually if you want and say 0.1. 1 divided by 10 is 0.1, and 1 divided by 15, I think, is 0.6, 0.0667. Boy. And that is equal to 1/v. So you could literally do it like that. Alright, so whichever way you're comfortable with, just work it out whichever way you're comfortable with. Yes, go ahead. Yeah, man, so we'd have to, so I say calculate this first and then do the reciprocal. So it would be, alright, 0.033. Well, it's not centimeters yet because it's still 1/v, so we can do, as you were saying, the reciprocal. So if we do the reciprocal now, because we don't want 1/v, we want v. So v is going to be equal to 1 divided by the 0.33, the 0.033. What is that? What you got? Anyway, how much I got? 1 divided by. So work that out and tell me what you get. So 30.3 cm. Alright, any problems with that working out? So all you're doing is just using the length formula. It's just that it's a bunch of fractions. So just make it simple for yourself. Alright. Some people they go ahead and find LCM, but if you know you can't bother with that. So some people just find the LCM and just work it out. You don't need to do all of that. You just put in the calculator and find a value. So I want to all right. So the next question, next the next question is to determine the magnification of the image formed. So the magnification of the image formed. Remember how we calculate magnification? How do we calculate the magnification? Alright, so image size over object size. So magnification. But in this case, we don't have the image size, we have the image and object distances. So we can use that as well. So we can use image v over u. Image. So what was the image distance again? That would have been what we just calculated. So image. Alright, and then over the object. So do that calculation. What does that work out to? That kind of already seem like a certain answer to me already. So magnification of the image. So by what factor is the image magnified? That's what you're working out. So it's basically 2, but basically 2.02 you say. So that's the magnification. For these, alright, for these we typically use the significant figures in the question. So significant figures meaning if you look in the question, in the actual question, well, I keep hearing something. So if you look in the question itself, what's the significant, if you were to look at the values of the quantities at the state, it's to two significant figures. So you can use that as a guide. So they want the answer, keep your answers to two significant figures as well. Alright, so it's not like the table where you're looking at the decimal places of everything else, you're really looking at the significant figures. So the first answer, we could have just left it at 30. 30 would have been two significant figures here. And 2.0 would have been two significant. So 15 is two significant figures. You just can leave it at your answer at two significant figures. 10, two significant figures. Alright. Alright, so I wanted you to so remember what the image distance is 30 and the magnification was 2.0. So I wanted to relate this to the diagrams that you saw earlier. Let me show you how you can predict these things. So the focal length here is 10. So then I'm going to go back and forth between alright. So what we just did a while ago is so I wanted to understand this table. We just did the 1, 2, 3, 4th we did a situation where you had the fourth row. So can you see that the situation that we just did was the fourth row? Can you see that? The situation that we just did was the fourth row. Alright, how can I tell? Yes, go ahead. Sorry, repeat. Oh, sorry. Okay. Um, so the focal length in the question was 10. I remember U is for object distance. So what they're saying is that if the image is greater than the image distance is greater than the focal length but less than 2 times the focal length, it will have these properties. Alright, so hopefully you're understanding this. So let me give an example of each of the case. Well, the first case is just infinite, so can't give no number for that. For the second row, this situation is if the object distance is greater than 2 times f. So 2 times f in the situation would be 20. So if you place the object at a distance like 30, that would fit this criteria. So the object distance is now at a distance that's greater than 2 times f. If you have a situation like that, the image formed is going to be inverted, real, and diminished, meaning it's going to be smaller than the object. If you put the object, at 2 times f, so if you put the object at 20, exactly at 20, you're going to have an image that's inverted, real, and the same size. So no magnification really. And then if you put the object between f and 2f, which is what that one is saying, between f and 2f is going to be inverted, real, and magnified. Alright, you will get a virtual image, from a convex lens if the object distance is less than focal length. Alright, if it's less than focal length. So you have some examples there. So a magnifying glass produces a virtual image that's magnified and upright. So a projector would produce an image that's inverted, real, and magnified. And photocopy as would do same size, and so on. Your eyes, and so on. So let me. It wasn't 220. Alright, so let me go back to, yes, it was 220. Alright, so this says state the nature and position of the image formed. So what did they want you to tell them here? So when we calculated, we got an image distance of 30 and our magnification was 2.0. State the nature and position of the image formed. I see 3 marks there. What are some of the, what's the nature, what's the position of the image formed? So you already calculated one, so you know how the image is relative to the object. So what's one feature you can talk about the image that you calculated already? You must know at least one of them. So the image formed was what? Was it? Mm-hmm. Mm-hmm. And the magnification was what? Again. Right. So if the magnification is 2.02, what happened to the image? What happened to the size of the image? So that's one of the things that you can talk about. What happened to the size of the image? So it's three things that can happen. Go ahead. Yeah, so the image would have gotten bigger, or we can say it was magnified. So can either say it stay the same size, be diminished, or um, be magnified. All right. So one thing you can comment on is if it's real or it's virtual. That's another thing you can comment on. All right. Now, if you know if it's real, so that would be the nature of it. State the nature would be whether it's real, if it's a real image or a virtual image. So it's going to be a virtual image if the object distance or if the object is placed at a distance less than the focal length or equal to or less than the focal length. So if this image, yeah, go ahead.